Production LLMs can delight users 1 minute and burn budget the next. In this module, we'll connect autoscaling, capacity planning, and FinOps, so your systems can handle demand reliably without letting cost growth run the show. We've already covered production architecture, deployment, observability, reliability, governance, security, and the mechanics of GenAI cost. Now we bring those pieces together as an operating model, scaling infrastructure, planning capacity, tracking spend, enforcing budgets, and running GenAI FinOps. Scaling an LLM application is not the same as scaling a standard web service. Bottlenecks can appear in app pods, model endpoints, GPU memory, queues, retrieval systems, or provider rate limits. The goal is to scale the layer that is actually constraining the user experience. If latency is high, more API replicas may not help if the vector store is slow or the GPU is saturated. Tie scaling decisions to SLOs such as latency, availability, response quality, and error rate. Then balance reliability with cost, so peak demand is handled without unnecessary over-provisioning. Kubernetes HPA is useful, but default signals can be misleading for LLM services. CPU and memory may look stable while users are waiting in queues, sessions are piling up, or token generation is slowing down. Use HPA for stateless API pods, middleware, and orchestration layers, and feed it custom metrics such as requests per second, active requests, queue depth, P95 latency, and tokens per second. Set minimum replicas for readiness and maximum replicas for cost control. Pair autoscaling with readiness probes, disruption budgets, and controlled rollouts so capacity changes remain predictable. Some workloads are better scaled from a queue. Ingestion, embeddings, evaluations, and batch summarization can often wait in a backlog. For these, scale workers based on backlog depth, message age, or processing lag instead of CPU alone. Serverless can work well for sporadic events because you avoid paying for idle capacity. But cold starts can break tight latency goals. The design principle is separation. Keep user-facing requests on a fast, predictable path and move heavier work async. Where startup time matters, use warm pools, provision concurrency, pre-initialized clients, and lightweight containers. GPU autoscaling follows a different logic because the limiting resource is usually accelerator capacity, not request count. Track GPU utilization, memory, batch queue depth, tokens per second, and model load time. Then connect those signals to model choices. Larger models, longer context windows, and lower quantization reduce how many requests fit on one GPU. Strong capacity planning also uses dedicated GPU node pools, placement rules, and replicas to avoid fragmentation. And because GPU capacity can be scarce, quotas, regional shortages, or price spikes should trigger fallback models or alternate providers. Autoscaling helps, but it is not a safety strategy by itself. During a demand spike, every shared dependency needs admission control. Gateways, services, routers, inference nodes, vector stores, and third-party APIs. Rate limits and token buckets slow intake. Priority queues decide what goes first. Circuit breakers keep failures from spreading. Backpressure tells upstream components to wait, retry later, or degrade gracefully. That may mean a smaller model, shorter context, cached answer, or async fallback. Reserve capacity and quotas for critical tenants, so overload becomes controlled service reduction instead of collapse. Capacity planning starts with a forecast, but the forecast has to become engineering numbers. Estimate users, requests, token volume, ingestion rates, and scheduled batch work. Translate that demand into throughput, requests per second, tokens per minute, embedding jobs per hour, and vector queries per second. Then map those numbers to real capacity. App pods, queues, model endpoints, GPU nodes, vector databases, and provider quotas. Finally, prove the plan before users do. Run load tests, replay production-like traffic, benchmark bottlenecks, and adjust scaling thresholds until the system has safe headroom. For GenAI, plan around the worst moments, not the average ones. Averages hide the bursts that break latency, drain token quotas, or exhaust GPUs. Use P95 and P99 request and token rates, then add predictable shocks such as launches, seasonal events, business hour peaks, and overlapping batch jobs. Set latency targets by workflow. Chat needs fast response, agents may tolerate longer orchestration, and document or evaluation jobs can often run asynchronously. Leave headroom for retries, failover, background work, and surprise traffic. If capacity ends at the forecast, you have already planned an outage. Resilience planning assumes normal capacity may not be available when you need it most. For GenAI systems, recovery objectives should go beyond classic RTO and RPO. Include failover latency, acceptable answer quality degradation, and incident mode spend. Reserve capacity where it matters: gateways, orchestration layers, model endpoints, and vector indexes. If continuity is critical, avoid single region or single provider dependency by validating secondary regions, fallback models, and alternate retrieval paths. Then test it. Failover drills and controlled load simulations reveal quota gaps, routing mistakes, and cost surprises before a real outage does. Cost optimization begins with request-level visibility. For every LLM call, capture the model, prompt version, input and output tokens, cache status, retries, latency, tenant, team, endpoint, and estimated cost. Connect those signals to quality outcomes such as task success, resolution rate, and user satisfaction. This avoids a common mistake: lowering spend while making the product worse. The most useful dashboards go beyond token totals. They show cost by workflow, customer segment, team, and environment, and translate spend into cost per successful task, user, or resolved issue. Cost control is also an operational safety layer. Set budgets for each app, team, environment, tenant, and model, and alert early as usage approaches limits. Watch for unusual patterns: output tokens jumping, retries spiking, or cache hits dropping. When risk appears, controls such as quotas, rate limits, approvals, and context caps can stop bugs, abuse, or runaway loops before they become expensive. FinOps becomes actionable when GenAI costs are tied to the people and products creating demand. Start with every relevant cost pool: model APIs, GPUs, vector databases, logging, shared infrastructure, and platform operations. Use consistent metadata such as application, team, tenant, model, environment, and workflow to allocate costs fairly. Showback makes spending visible so teams can understand patterns and optimize behavior. Chargeback goes further by assigning actual budget responsibility. The goal is not punishment. It is clearer ownership, better trade-offs, and fewer hidden subsidies across the business. GenAI FinOps works best as an operating cadence, not a one-time cleanup. Teams regularly measure usage, analyze cost drivers, optimize choices, govern changes, and review outcomes. Engineering examines model selection, routing, prompts, caching, batching, quotas, and latency trade-offs. Finance and product connect those choices to unit economics and customer value. Security and governance make sure approved models, fallback paths, compliance rules, and quality benchmarks are respected. Vendor management belongs in the loop as well, including pricing, commitments, reserved capacity, and negotiation leverage. The goal is disciplined cost reduction without sacrificing accuracy, safety, latency, or user trust. Production GenAI succeeds when performance, capacity, and cost are managed together. Scale from real workload signals, not guesses. Plan for peaks, quotas, latency targets, and recovery. Make cost visible at the request level. Then use budgets and alerts to act early. Finally, keep reviewing models, vendors, and trade-offs so optimization becomes an operating habit.